In the case of a weak acid situation like this, we know that we've got this equilibrium where the weak acid dissociates to a very small extent to form H plus and A minus. And we know that the Ka expression for that equation is certainly the concentration of H plus times the concentration of A minus over the concentration of HA. Okay, now if we rearrange this equation a little bit and then take the negative log of everything, and again, you don't need to know how to do that, but basically if you start with this, rearrange it, and take the negative log of everything, what you end up is you end up with this equation right here, and this is the last equation that we need to know. That's the only equation that we haven't discussed yet that's on the equation sheet that you absolutely need to know how to use. Okay, now this is a super duper important equation. There's a lot of questions that, again, haven't been asked in your homework yet because so many of the buffer questions deal with the knowledge, not necessarily doing the math, but the knowledge of this equation here. Okay, this is called the Henderson-Hasselbalch equation. Some people just abbreviate and call it the HH equation. Doesn't matter what the name is. Okay, this is used very commonly when you're dealing with a buffer solution. Okay, there's lots and lots of different ways to use it. So first of all, we can see that the pH of the solution is equal to the pKa. So you take the Ka, and remember the pKa, just like the pH, is equal to the negative log of the Ka, which is how the Ka became the pKa. We took the negative log of this whole thing. Okay, and that, again, plus the log of the conjugate base, so there's the concentration of the conjugate base over the concentration of the original acid. Okay, and then there's one for a buffer solution as well, where again, you've got the concentration of the just remember, the conjugate goes on top. This is the conjugate acid on the top, and this one is obviously the original base. On this one, the acid goes on the bottom, and what goes on the top? It's conjugate base. So remember, the conjugate always goes on top, the one with the negative charge, or in this case, the one with the positive charge. And then the normal base, or the normal acid, goes on the bottom. Okay? Now, how do you use this equation? Again, lots and lots of different examples of how you use this. You're going to use this with titrations. You're going to use this with normal buffer solutions. Again, you typically use this equation here. This is the only one that's given on the AP exam. The base one is not. The POH one is not. And that's fine. Again, if you know the acid one and you know how to use the acid one, that's perfectly fine. So some of the ways you're going to use this equation is, first of all, let's think about when we first started doing a titration. Okay, when we first started doing a titration, let's kind of go back here a little bit to, let's say we started, and I'm not going to do, let's just do 6 of them. So 3, 4, 5, and 6. So when you start a titration, you start with all of these acid particles. So you've got HA, and then you start to add some base to it. So here comes the OH minus that's going to start coming in here. And again, when we know when that happens, that the H plus, or the HA, starts to turn into H2O and A minus. Okay, so let's think about this equation right here. At the beginning of the reaction, this number is really big, and this number is really small. Okay? And as the titration continues, the concentration of the acid starts to go down, and the concentration of the conjugate base goes up. As you add more hydroxide, more and more of these HA particles are going to turn into conjugate base particles. Okay, and remember, we're going to get to a really important point here where during the titration, all of a sudden, the concentration of the acid particles, there's 3 of them, is equal to the concentration of the conjugate base particles. they're equal to each other. So what does that mean? It means when they're, and we should remember, what's that point called in the titration where the concentration of the acid is equal to the concentration of the conjugate base, is the half equivalence point. Okay? And at that point, we know that the concentration of A minus and the concentration of HA are the same. And if they're the same, then what happens is whatever this number is the same. And what that means is that that number is equal to 1. And the log of 1 is equal to 0. So, at the half equivalence point of a titration, this whole part here cancels out, and the pH is equal to the pKa. Okay, and they really like asking questions about that, about your ability to identify the half equivalence point, your ability to look at a titration curve and determine what the pKa or the pH is based on the half equivalence point of that reaction. Okay, and again, we'll see some examples of that here in just a second. Okay, so let's talk a little bit more about what I just said. So since the pKa or pKb is fixed for a weak acid or base, if the concentration of the components are changed, but remain in the same ratio. So let's say the concentration is 0.1 and 0.1 or 0.5 and 0.5, well, then the pH of the buffer doesn't change. However, when you change the concentrations of the components, that does affect the capacity of the buffer. We know that, okay? So a 0.5 has a greater buffer capacity than 0.1. We talked about in the last video. Okay, now let's talk about the acid version. So, and again, this is the one they normally use. Okay, it can see that if the pH of a buffer solution is greater than the pKa of the acid. Okay, so let's think about that. Let's come back up here to the math. If this number is bigger than this number, so if the pH is greater than the pKa, what does that tell you about this right here? Okay, it tells you that, again, remember that the log of a number that's bigger than 1 is positive. The log of a number that's less than 1 is negative. That's all you have to know. The log of 1 is 0. The log of a number greater than 1 is positive. Okay, and the log of a number that's less than 1 is negative. So if this number here is greater than this number, that means that this number has to be positive. And if that's going to be positive, it has the fraction has to be greater than 1, which means you have more A minus than you do HA. Okay, and again, think about in a titration situation, what does that mean? It means you're past the half equivalence point. Okay, if you now have more conjugate base, if you now have 4 of these and you have 2 HAs left, that means the concentration of A minus is greater than the concentration of HA. And you're past the half equivalence point. So if the pH is greater than the pKa, again, in terms of a titration, you're past the half equivalence point. Okay? And the opposite is also true. If the pH is less than the pKa. So again, if this number here is smaller than this number, then that means this has to be negative. And for that to be negative, the fraction has to be less than 1, which means HA has to be greater than A minus. So, and the only time that HA is greater than A minus is before the half equivalence point. So that means you are before the half equivalence point. Okay, and then of course, if the pH is directly equal to the pKa, then you are exactly at the half equivalence